So we've talked about the differentiation rules, and specifically the differentiation rules gave us a way to take the derivative of the sum of functions, constant multiple of functions, the product of functions, and the quotient of functions. But there's another very important way to combine two functions that we have not discussed, and that's the composition of two functions. So what is the idea behind function composition in taking derivatives? Well, the idea is called the chain rule. So let's say that f of x is a function that's differentiable at g of x. And g of x is a function differentiable at x. Then the chain rule states that the composition, so f composed g of x, is differentiable at x, and furthermore, we actually have a formula for the derivative. So f composed g prime of x is the following. So it's f prime of g of x times g prime of x. And if you're a little uncomfortable with this notation, recall that f composed g can also be written like this. It's f of g of x. And that's really what we're taking the derivative of. So the idea behind the chain rule is if you're taking the derivative of a function that has an inner function that you're composing with an outer function, f, the derivative is given by f prime, so you take the derivative of the outside function, leave the inside function alone, and then multiply by the derivative of the inside function. So there's another way to think about the chain rule using the idea of rates of change. So let's say that y is a dependent variable that varies with u. So u here is another variable, and u varies with x. So in this situation, u is sometimes called the intermediate variable. And then x is called the independent variable, just as before. So we see that y is the dependent variable. It depends on this intermediate variable u, but u is also a dependent variable in the sense that it depends on the independent variable x. Okay, so let me write this symbolically just so you can see. So I'm saying that y is a function of u, and u is a function of x. Okay, then if we want to know the rate of change of y with respect to x all the way down the chain, that's why it's called the chain rule, then what we do is we first find the rate of change of y with respect to u, and then we multiply by the rate of change with respect to x. Okay, and so it's really easy to remember the chain rule in this form because you sort of can just cancel the du's in some sense, right? If I cancel the du's, I'm left with dy dx. Now that's not exactly correct, but it is a good way to help you remember the chain rule in the rate of change form. And so the chain rule is going to allow us, first and foremost, to take the derivative of a wide range of functions that are formed by composing functions with other functions. So we're going to see that this is an extremely useful technique, and it's very important to remember. So the best way to get the hang of the chain rule is just to see some examples, because it's one of those ideas that you just need to get the feel for it through practice, and then it becomes really natural to do. So we want to take the derivative of this function f of x. And for the first few examples, we're going to be very explicit in showing that yes, this actually is a composition of functions. So what I can do is I can think of sine of e to the x as sine of u, where u is e to the x. So we really have an outside function, so sine of u, and the inside function that we're composing is e to the x. And so the idea of the chain rule is really simple. The derivative is just, I ignore the inside part. So I just ignore the u for a moment, and just take the derivative of sine. So what's the derivative of sine? It's cosine. So f prime is cosine, and then I just leave whatever I was taking the sine of. So now it's cosine of e to the x. So this is really like if I write this as a composition, this so if y is sine u, then what we're saying here, this is dy du. And then the price is we have to multiply by the derivative of the inside. But the derivative of the inside is e to the x. And this is really like du dx. So you see the derivative is the derivative of the outside function, or the rate of change, if you want to think about it that way, with respect to the intermediate variable u. But u is really e to the x. So then we multiply by the derivative, or the rate of change of u with respect to x. So the derivative is this. So this is kind of a couple different perspectives in one. I encourage you to just kind of latch on to whatever makes the most sense. For some people, it makes the most sense to actually explicitly write u here and write what u is. Some people don't like to do that. Some people just like to think, okay, I need to take the derivative from the outside in. Take the derivative of the outermost function, then multiply by the derivative of the innermost function. And if you have to do that multiple times, that's fine. So let's see another example with this g of theta. And now recall that tan cubed theta is like tan theta to the third power. And again, I can think about y being u cubed, where u is tan theta. So the derivative, g prime of theta, the outermost function is like u cubed. So if I take the derivative of something cubed, I use the power rule. I bring down the 3. I leave the inside alone and decrease the power by 1. But then the price is I have to multiply by the derivative of the inside, so the derivative of tangent theta. But the derivative of tangent theta is secant squared theta. So here's the derivative. And if you like to use the intermediate variable u, just note that this is really dy du times du d theta. Okay, so that's the chain rule. And of course the examples get a lot more complicated, but the idea is the same. You work from the outside in. All right, so now we want to find the rate of change of y with respect to t. So dy dt. And this example is actually going to show how the chain rule can be used to simplify the procedure of taking the derivative. So what I want to do here is I want to actually just set u to be this inner function here. So notice that y really is like the composition of this inside function, t squared over 2 cubed minus 4t, and the outer function, which is raising to the third power. So u, we're going to say, is t squared over t cubed minus 4t. But then y is just u cubed. Okay, so then what is dy dt? It's just going to be dy du times du dt. That's what the chain rule says. Okay? And so dy du is really simple. Dy du is just, well, 3u squared. Or, okay, what is u? U is really this t squared over t cubed minus 4t. So 3 times t squared over t cubed minus 4t squared. Okay, so dy du, we of course want to leave everything in terms of t to have the derivative as a function of t. This is just going to be 3 times t squared over t cubed minus 4t all squared. And now we just need to multiply by du dt. So what is du dt? Well, this takes a little bit of work, but it's not too much work. U is a quotient of two polynomial functions. So du dt we should find by using the quotient rule. So du dt is going to be low d high, so t cubed minus 4t times 2t minus high d low. So high is t squared, and the derivative of the bottom is 3t squared minus 4. All right, and then all over the bottom squared. So t cubed minus 4t, that quantity squared. Okay, and so actually this numerator simplifies just a little bit. So what do we have? We have t cubed times 2t, so that's going to be 2t to the fourth. This is going to be minus 3t to the fourth. So all in all, we have a minus t to the fourth. Okay, Then we have minus 4t times 2t, so that's minus 8t squared. And then we have minus 4 minus t squared times negative 4, so it's going to be plus 4t squared. So it looks like we're going to get in total minus 4t squared. Okay, and it looks like that's all we have. So then that's all divided by t cubed minus 4t squared. And we'll leave it at that. So here's the derivative of this function, or the rate of change of y with respect to t. So we took the derivative of the outermost function, left the innermost function, then multiplied by the derivative of the innermost function. Okay, so this is a little bit more intricate, and what we're going to notice here is that we're actually going to have to use the chain rule multiple times. So let me first simplify it for you. Let's actually just set u to be the square root of 1 plus square root of t. And notice that one of the first steps when you're doing a chain rule problem is to identify what is the innermost function. Well, in this case, the outer function is sine. Now I'm multiplying by 4. That's going to be okay. I can just use the constant multiple rule. But the outermost function is sine. And we're taking sine of this inner function, which is square root of 1 plus square root of t. So y is just 4 sine of u. We'll notice that dy du is now pretty simple because u we sort of absorbed in this complicated expression. So the derivative of y with respect to the intermediate variable u is 4 cosine u. Okay, but we also know that we need to take the derivative of u with respect to t to use the chain rule. So let's find du dt. Well, I'm actually going to do something very similar. So I'm actually going to let m equal 1 plus root t, because I'm recognizing that u actually is a composition of functions. It's a composition of the square root function with 1 plus square root of t. So u is really like square root of m. And notice here what I'm doing is I'm just trying to break it down into small pieces. Now this isn't really necessary. You can sort of do all of this all in one step, but I want to be very careful and just show you the idea of these intermediate variables in the chain rule. So if u is square root of m, then what we have next is du dm is going to be what? Well, recall that square root of m is m to the 1/2. So we're going to bring down a 1/2 and be left with m to the minus 1/2. But that's the same thing as 1 over 2 square root of m. And so all I'm saying is that this is the same thing. So when I take the derivative of m to the 1/2, I get 1/2 m to the minus 1/2, but that's the same thing as 1 over 2 square root of m. Okay, so we're not quite done. We also need to take the derivative of m with respect to t. But this will just do. So dm dt is going to be 0 plus the derivative of square root of t. But we just found that. That's going to be 1 over 2 root t. Again, just using the fact that square root of t is t to the 1/2 and applying the power rule. Okay, so then du dt is going to be du dm times dm dt. okay, which is 1 over 2 square root of m, but m is 1 plus root t, and then times dm dt, which is 1 over 2 square root of t. That's what du dt is. Now we can finally go back and figure out what dy dt is. So dy dt, by the chain rule, is dy du times du dt. Okay, dy du is 4 cosine u, but u is square root of 1 plus square root of t. And then we multiply by du dt, which is 1 over 2 square root of 1 plus square root of t times 1 over 2 root t. So this whole nasty expression is dy dt. And notice the role of the intermediate variables of using this u and m. It took this very complicated function to take the derivative of and broke it into a bunch of small steps where the derivatives were manageable. So that's the idea of the chain rule. And it's important to remember, of course, that you may have to use the chain rule multiple times. All right, so we want to find the second derivative here. And remember, it's really easy to find the second derivative once you find the first derivative, because the second derivative is just the derivative of the first derivative. So let's start by just finding the first derivative. Okay, so y prime is just going to be the derivative of this with respect to x. So we have e to the x squared. Now that's a composition of functions. So if we think about this as being e to the u, where u is x squared, then the derivative is going to be just e to the u, so e to the x squared, times the derivative of x squared, which is 2x. Okay, so I'm thinking about the outermost function as being this exponential function to base e, composed with the function x squared. The derivative of the exponential function, so the derivative of e to the something, if you like, is just e to that something, but then the price is to multiply by what was in the argument of the exponential. Alrighty, and then plus derivative of 5x, that's easy, it's just 5. Recall that this is x to the first, so we bring down the 1 and it becomes x to the 0, which is just 1. Okay, so there's the first derivative. So the second derivative, like we said, is just the derivative of the first derivative. So here, we actually have a product of two functions. So we got to use the product rule. So we got to take the derivative of e to the x squared, but we already know that that's e to the x squared times 2x. So that's the derivative of this function times the second function, and then plus the first function times the derivative of the second function, which is 2. And then plus derivative of 5, that's a constant, so the derivative is 0. Okay, so this is the derivative. Sorry, the second derivative is the derivative of the derivative. And now we could simplify, but really there's no need, right? Because this is the correct answer, it's the derivative. I'm happy with that. And notice that we actually had to use the product rule here as well as the chain rule. So a tricky thing about derivatives is that a lot of the differentiation rules will start coming into play. Alrighty, so we're trying to find the second derivative again. So no magic. We'll start by taking the first derivative. So we notice that y is a composition of the function sine, that's the outermost function, sine, and then the inner function is actually a product of two functions. So we start by taking the derivative of the outermost function, which is sine. So the derivative is going to be cosine, and then we leave the inside alone. And then the price is to multiply by the derivative of the inside. So to multiply by the derivative of x squared times e to the x. But like I said, this is a product of two functions. So we take the derivative of the first times the second plus the first times the derivative of the second. Okay, and this is the first derivative. Now I'm not going to simplify this, and you're going to see why. And you're really going to see, at least in these examples, simplifying doesn't always help you. So I want to take the second derivative, so the derivative of the derivative. So let's be careful here. I'm going to notice that actually here I have a product of two functions. This function times this function. So let's use the product rule. So this should be the derivative of the first function, which is minus sine x squared times e to the x. Okay, that's the derivative of the outside function, times the derivative of the inside function, which is, well, we already did it. It's 2x times e to the x plus x squared times e to the x. Okay, that's the derivative of this function. And then the product rule says we need to multiply by this function. But that's the same as this function, so it'll just be that squared. And then plus the first function, so cosine x squared times e to the x, times the derivative of the second function. So what's the derivative of the second function? Well, we have two product rules. So the derivative of this guy is going to be 2e to the x plus 2x e to the x. Okay, so that's the derivative of the first times the second plus the first times the derivative of the second. And then plus the derivative of this guy. Derivative of the first is 2x times the second plus the first times the derivative of the second. But the derivative of e to the x is e to the x. Okay, and believe it or not, we are done. So it's a little messy, but that's okay. We're not going to sweat it because this is the second derivative. So as you can see, a seemingly innocent composition of these two relatively simple functions, when you start taking derivatives, things can get very complicated. It's very tricky to remember to keep applying the chain rule, to apply the product rule when you need to. So the trick with derivatives is to be very patient. And notice also that those tricks of using the intermediate variables. So if we let this be u and then kind of take the derivative of that separately is actually really helpful. Now notice I didn't do that here. I sort of did it the lazy man's way. I did it all without kind of separating, okay, this is a composition of this, this is sine of u. That might have been really helpful here, but I mean, to each his own. Just find a way that works for you.